Hello and welcome to this MM3 CAE presentation on design optimization. What capabilities do the latest CAE tools offer? Traditionally, engineering design was mainly pen and paper based, with calculations being performed on basic calculators. Recent advances in IT technology have accelerated the design process by using computer software to design components in 3D and optimize their structures. Because of this, CAD software is now widely used in industry as a standard basis for engineering design. Software packages have become more user-friendly through the use of improved user interfaces and the lack of complicated computer language. 3D software has even become available on mobile platforms such as the Apple iPad. Services such as Dropbox, Google Documents, and Microsoft OneDrive allow for mass sharing of design files. This improves the efficiency of design as people have access to models and other files wherever the internet is available. This visual representation demonstrates that the larger costs in a project present themselves at later stages, such as prototype production. The price of CAD software may seem like a costly investment, but the amount of time and money that is saved in design by using it makes it a cost-effective solution. There are three main groups of CAE tools: pre-processing, analysis, and post-processing. Pre-processing can involve 2D drafting, electronic and circuit design, and even building design. 3D modeling is the main use of software in mechanical engineering pre-processing. Using design software in the pre-processing stage allows for designs to be adapted quickly should requirements change. It is relatively simple to eliminate problematic features of a design at this stage, something that would consume a lot of time and money if left until the prototyping stage. Also, processes such as shelling or editing the thickness of specific sections allows for the weight of a design to be easily controlled. The cost-to-weight ratio of any component may therefore be optimized as a result. In manufacture and assembly, certain features are essential to allow for ease of production. These characteristics are easily implemented in design software, with most having specific tools for each. Once a model has been produced, creating a matching drawing of the part is a simple task. The drawing scale can be controlled, and different drawing features may be utilized with ease. This functionality reduces the time involved in the design process, as traditional engineering drawings had to be drawn by hand.
After pre-processing, the CAE software allows for analysis of your designs, such as finite element analysis. Once the product has been modelled, various forces can be applied in a virtual environment, and the product then reacts to simulate the real world. The effects of mechanical stress, vibration, fatigue and more can all be modelled using finite element analysis. This allows potential problem areas to be identified and helps to predict if and where the design will break or wear out. FEA works by dividing up the model into lots of small, finite pieces or elements. Each element is defined by its corner points, which are known as nodes. One analogy is the idea of lots of tiny straight lines being used to approximate a larger circle. The behavior of each small element can be described by the displacement of the nodes, and using knowledge of materials, an expression in terms of stiffness can be formed. The elements are then combined to predict mathematically how the whole model will react to external or internal forces. Very complex objects and structures can be modelled this way, but by focusing on critical areas of the object and ignoring the less important parts, you get more information on the bits that matter and less non-essential information. This saves time, as very complex models take a very long time to analyse. The most common uses for FEA analysis are in the aeronautical, biomechanical and automotive industries. The reason finite element analysis is useful is it aids design evaluation. It can predict how the object will react and perform in real life. Problems that would otherwise be found in the prototyping stage are now identified earlier on and can be corrected easily without the added time and cost of building and prototyping each iteration of the design. The designs can be tested in lots of different materials to see which performs best. Once a high stress region has been identified, the design can be altered to reflect this new information, and material can be removed from low-stress regions to save materials, weight, and money. Information traditionally gained through prototyping and testing can now be done in a virtual environment, again saving money and time. It provides a prediction as to whether the design is capable of meeting the requirements. However, FEA does have its limitations. The software is often very expensive and skilled technicians are needed to operate and interpret the data. The objects and structures are simplified models of the real thing, and as such there is an element of estimation. If not interpreted with this in mind, problems could arise later in the project if a mistake has been made. There are various options for CAE packages capable of finite element analysis. The packages also cover many other types of analysis, such as multi-body system dynamics.
Finite element analysis is something that is constantly developing and improving. Recent CAE software has seen finite element analysis move from single parts to linked systems, known also as multi-body systems. The analysis of such systems is known as multi-body system dynamics. A multi-body system is a system of solid bodies or links connected by joints. The motion of each body is restricted by the bodies it is conjoined to, thus forces and loads on one element are spread through the system via these joints. Multi-body system dynamics is used to understand how elements of a system react with each other and also how the system reacts with the environment, which is particularly useful for vehicles as different terrains will react differently under the load of the vehicle. The main use of a multi-body system dynamics software is within vehicles and machinery, testing if the design is safe to operate for a required time without failing whilst meeting performance requirements. Another big use of the software is in the designing of dampers, as the analysis software is useful to predict the loading on the dampers. MSD software is available for gear trains, analysing how stresses are transferred through complex gear systems. So why do we use multi-body system dynamics analysis software? The first reason is because multi-body systems are able to produce loads larger than expected, especially when the body is moving, and these are difficult to predict. Overloading parts could compromise the safety of the user. Current systems are so complex that estimating the transfer of a load through it is a very long-winded process, and so it's much easier to have the software carry out the test for you. This saves time and money in the design process, making the product much more profitable. Most modern-day design requirements would be near impossible to meet without the use of multi-body system dynamic software. Recent MSD software not only improves the system in terms of safety and performance, but is now also used to improve the comfort for the system operator. And MSD software has now stretched to include the effects of vibration and noise on a system, and control system integration can test the long-term effects on a system. Many engineering products are controlled by an electronic control system, be it from a washing machine to the cruise control on a car. It's useful to test the effects that running the system over time will have on the product. Whilst finite element analysis of a shaft will show that it can carry a certain load, it cannot prove that it can operate over, for example, 100,000 cycles. MSD analysis allows a control system to be created and programmed in MATLAB or Simulink and ran for the life of the product to predict the long-term effects of usage. There's lots of MSD software available at the moment. The most popular two packages are MSC Adams and Autodesk Simulation Mechanical. There are also specialist programs out there, for example Driver, which is used to model wind turbines and such under the random forces of the wind. Also, Transmission 3D is a gear train analysis software. It accommodates all gear types from basic helical through to complex worm gears, alongside incorporating the effects on the bearings, shafts and the housing also.
Computational fluid dynamics software is practically a necessity for engineering products which deal with fluid structure interaction. It is used in many engineering sectors, from aerospace to marine engineering. CFD optimization is a strong tool and has the advantage of visualizing fluid flow, since it is otherwise invisible to the naked eye. Key optimization targets are the reduction of drag, greater control of fluid flow, and the minimization of cost. These are the most commonly used software, and they all have their own special functions. Shape optimization software, for example, such as ANSYS CFD, automatically adjusts the geometric parameters of a specific design until specified optimization goals for the design are met. An example of CFD optimization is a high-quality Speedo swimsuit, which has been used numerous times in high-caliber sporting events such as the Olympics. The aim was to reduce drag and aid the swimmer's performance as much as possible. Various materials and designs were analysed using the CFD software ANSYS.
The end result was a high-quality swimsuit which reduces drag by a considerable margin and physically compresses the swimmer's body to make them more aquadynamic. Displayed here is a time-lapse of the shape optimization process for a high-speed race car. It shows how geometric parameters of a design are iterated until the optimum value for a property, in this case downforce, is achieved. This video shows a simulation of airflow around a commercial car. This is an important aspect of design for the automotive industry since a reduction of drag leads to a reduction of fuel consumption, resulting in a positive contribution to the overall efficiency of the car. Shown here is the analysis of temperature regulation for a large supermarket. This demonstrates a broad scope of engineering disciplines which CFD optimization is used for. Safety analysis is a very important part of all engineering projects since health and safety is always paramount. This method of optimization is most commonly used in the automotive industry, but it is also used in the aerospace industry. Simulation applications such as crash safety and accident reconstruction are very important for car manufacturers. They allow numerous car designs and collision types to be analysed extensively and in great detail. The tests are much quicker than the older physical crash test method. Computer simulation methods are not yet fully reliable, and so physical tests are still carried out to this day. However, as CAE tools become more advanced in the future, it is seemingly likely that all crash tests will be carried out digitally. Software such as LS-DYNA, ANSYR, HyperWorks and Madimo are used for safety analysis simulations. Madimo is a software which offers an adjoint solver. This particular function provides insight into how to modify geometry to achieve design goals. It provides information in a single simulation, data that is difficult and expensive to gather using other methods by computing the derivative of engineering quantities with respect to the system inputs. An example of safety analysis is shown here, where the life and performance of road safety barriers was simulated. Impact severity parameters such as the strength and maximum deformation of the barrier were determined using both a computer simulation and a large-scale physical test. The image shown shows a very good agreement of barrier deformation and car behaviour for both analysis methods. This experiment gave evidence for the accuracy of computer-based safety analysis simulation, meaning that it may be relied upon in the future with greater confidence and reliability. Here is a demonstration of the very latest tools CAE can offer with regard to crash safety simulation. The software, 3D Excite, allows engineers to review the results of a crash simulation more easily, evaluate different design approaches, and approve engineering changes with more speed and efficiency. With the new technology, engineers can create and manipulate the simulation at a push of a button and complete it in hours instead of weeks.
In post-processing, there are two main categories, which are rendering, creating an image from the design model, and computer-aided manufacture, the use of software to control machine tools to produce a product. Rendering is defined as a processing of an outline image using color and shading to make it appear solid and three-dimensional. Basically, it is a quick and easy way to add texture and color to a design without the need for any artistic skills, as were essential in the past. This is a really useful aid to communication, helping present ideas without the need for a physical model. Software like Luxion's KeyShot allows you to import your design from any of the main computer-aided design softwares and easily produce interactive 3D-enabled rendered images. A screenshot of one is posted here. Computer-aided manufacture, the most vital stage of post-processing. Once you've designed, analysed, rendered, and are content, it's time to create the product. To do this, we need to use one of the many pieces of software which automatically converts designs into G-code, the language of CNC machines. Some companies, like ICAM, have software which analyzes the manufacture of the designs. ICAM's SmartPath technology optimizes the machining code to create the most efficient motions. This speeds up the manufacture of the part and minimizes overall tooling time, both of which contribute to a large cost saving. The aspects covered in this presentation all contribute to an optimized designing process. By optimizing, the benefits are clear. Speed. From design through analysis and manufacture, considerably less time is needed. Simplicity. The design process is now accessible to people regardless of their skill. Accuracy. Human error is nullified as much as possible, leaving a safer, more consistent product. Cost. The big one. The main factor in industry. By optimizing the design process and from the benefits above, there's a significant saving in the overhead for projects. This concludes our presentation. Thank you for listening.